Hey everybody! What we're going to do in this video is look at how to do a moderation analysis, so regression with interactions by hand. So in my previous videos in class we talked about how to do this using the quantsci package, which works great until you have to have multiple moderators. And so we have some problems in our lab currently where we have 3- and 4-way interactions, and so coding them by hand becomes important. So understanding that process and knowing how to do it so that you can apply that procedure to multiple moderators. So what we're going to do is take the same example that I covered in that class with only 2 variables just to make it nice and easy, and then you can take that from there and apply it to more complex designs. Alright, so first thing I want to do is just import this data. And what this data set has in it is a set of grades for a course, the number of books the person read that was assigned in the course, which runs from 0 to 4, and the number of times that they attended the course. So we're trying to see if there's an interaction between the number of books they read and their attendance, predicting their final course grade. So if I could look at a summary of that just to make sure that it looks okay, if you're looking at accuracy. So my books and my attendance aren't negative, which is good, and the grades aren't outside the range of things that you would see in a traditional class. So this data set looks pretty good. The first thing I'm going to do is scale the variables. Now you can do this here at the beginning or at the end. I'd recommend doing it here at the beginning. And this is actually something that you can decide not to do. So some people argue that you should always scale variables that are included in interactions, continuous variables. It does not make any sense to scale a categorical variable because they're categories. Why would you z-score categories? But some people argue you shouldn't. And I'm sort of half and half. I'm going to show you here how it's done scaled, but there are times when scaling makes no sense. So what is scaling? One problem that you have with adding interactions into an equation in a regression is multicollinearity. Now, in an ANOVA, we can add our interactions and it works out okay because each condition is a special combination. But when we get into regression, you can't have variables that are perfect linear transforms of each other, or you'll have what's called singularity. So this will happen when you say add the subscales and then add the total score. Those subscales add up to the total, and so it creates an undefinable solution because those subscores add up to the total, which is a whole lot of matrix algebra to say that you're dividing by 0. And so what we're doing when we introduce an interaction is actually creating multicollinearity because the interaction is a perfect, but a good transform because it's multiplying 2 columns together. And so one way to circumvent the addition of multicollinearity is to scale the variables. Now, people think of scaling as z-scoring. I'd actually recommend just mean centering. So what you do is you take each column minus its mean, and what that does is it creates the average score as a 0. And so it sort of shifts everything to 0, which means that at 0, we're talking about the average of that variable. So scaling really has 2 purposes. It reduces multicollinearity and it improves interpretation. In the sense that it means that when this x variable is 0, that is at the average of that score. Now, times that scaling doesn't make sense. We've been working on a project where scaling variables gave us b values that were totally uninterpretable. So it is a little bit more difficult because you're interpreting a variable that's been transformed, and that's always a little bit harder. Or if you just don't have multicollinearity problems, then keep it in the scale it's in because that makes it just a touch easier to interpret, because then the predictor's in the same range at least. So you can go either way with this. I'll show you how to work on scaling. Z-scoring would be kind of like making them beta, but here I've done the code just to mean center. So the scale function here will create z-scores if you leave off this, but what we want to do is just mean center the variables. So we're turning scale equals false to turn off dividing by the standard deviation. If I had left that out, or if I mark it true, this will create z. if I say scale equals false, it will just create us mean centered. So that means it'll take the average score and subtract the average from each person's score. Okay, so if you have a 0 now, that means you're an average number of books read or an average attendance. So I'm going to create those two here at the beginning, because what that does is it allows me to use them. So to run assumption checks in a real regression, we need to first run the final model. So the final model here is books times attendance. Okay. And they should be centered if we are going with centering here. So I've centered them. And I'm just going to use that to help me check for normality and linearity. Okay. So I've run my final model, y equals books times attendance, which will give me the main effects of books and attendance, all three variables. So that's actually got 3 variables, books, attendance, and books by attendance, on my main data set. Okay. Now, the only trick about doing them at the beginning is it does change the way you interpret outliers. But only in the sense that you can't just throw everything into Mahalanobis or you'll get a singular matrix error. Okay. So what I'm doing here is I'm telling it to only pull columns 3 through 5, because over here, if I look at my master data set, I want to use the y, the dv, and my 2 centered variables. It also shows you over here how it centered them, so scaled equals center, and it tells you what the average score was that it's centered by. So the mean here was 2, and the mean here was 14, which matches our summary statement. Okay. You can actually use either set. You can use these first 3 or these last 3, because all we've done is linearly transform these 2 variables. But for me, I'm going to stick with the variables I know I'm using, which are here my z-scored variables. So I've just done 3 through 5 on all of my columns here. If you have questions on how this data screening works, I have a couple videos for data screening that go over this in depth a lot more. And I'm sort of assuming that you've watched or you're at least familiar with data screening and regression. Okay. So we're going to run Mahalanobis, so we're going to get the distance from the centroid for all 3 variables. I'm going to create myself a cutoff score using 0.001, so I want the scores to be very, very far away from the middle before I say that they're outliers, based on the degrees of freedom of the number of variables that I'm using. So that cutoff score is 16 with 5 degrees of freedom. Oops, that's incorrect. Let's fix that real quick. It's actually 3 degrees of freedom. Okay, so this should match throughout here. Just missed that one. So that creates us a cutoff score of 3 degrees of freedom, 16 points. And what we're going to do is save those variables, save their scores. So it's either bad or not. And the direction here is that it will mark everyone whose score is an outlier as true. Then we're going to set that to numeric to keep tabs. So everybody who's an outlier will get marked with a 1. Everybody who's not will get marked with a 0. And we're going to use that here in a minute. And then because I like to ask my students how many outliers did you have, this will output how many I had. So I have no outliers based on Mahalanobis distance. Okay. That analysis will match if you use the z-scores or if you, the centered variables or the regular variables. You'll get the same answer. Now here, these leverage scores are based on these z values, so it makes sense to match my Mahalanobis based on z. So the number of IVs here is 3. If you're doing moderation, remember that every variable that you add creates another set of predictors. So if I have a 3-way interaction, I have all 3 main effects, 1, 2, 3, all the 2-way effects, 1 and 2, 2 and 3, 1 and 3, and then I have the 3-way interaction. So if you're not sure how many IVs this creates, just run a quick summary of that first regression that you had and look at how many variables there are. So there's 3 predictors, ignoring the intercept here. I don't want to look at this analysis because this still includes my outliers, but I can use it kind of quick and dirty to figure out how many predictors there are. If I have, like, let's say a 4-way interaction, it creates a lot of predictors, and you might, if you have categorical variables, that throws another wrinkle into the plan. So be sure you use the right K here. So 3 predictors. I'm going to create my leverage scores using the hat values function. Remember, leverage is the how much weight each person has on the slope. The cutoff score for leverage is 2k plus 2 divided by n. Okay, so let's see what that is. It's 0.2. Okay. So the more n you have, the smaller this gets. And we're going to save whether or not they're a bad leverage score, and let's look at how many we have. Okay. So I have 3 scores that are considered to have leverage on one of the slopes. And I would say leverage is really important because having a big change on the slope means that that one person is shifting the slope around. And every person changes the slope a little, but you don't want them to have that much influence. But just in case, we're also going to use Cook's. Cook's is a measure of both leverage and influence, which is a measure of leverage and discrepancy. So it's Cook's is an influence measure. It's a measure of leverage, which is similar to the leverage values, and discrepancy, which is how far away they are from the rest of the data. Okay. The cutoff score for Cook's is 4 divided by degrees of freedom error, which is n minus k minus 1. Okay. Our cutoff score for that one's 0.11. And let's see, we don't have anybody who's a bad outlier on Cook's. So leverage might be just a little too lenient. Cook's will help say, yep, they're bad, or nope, leave them alone. So we've got 3 different scores here. We're going to add those up, and 2 strikes, you're out. So anyone who has at least 2 markers of being an outlier here is going to get excluded, which is no one in this data set. Right? But here I'm going to just create, I use this code over and over again, so I've got it here just in case it does have outliers. You know, let's say I add more people to this data, or I'm using this standardized code for later analyses. And so I'm going to create myself a no out. Now that didn't do anything because I didn't have, as you can see down here, any outliers, but it allows me to kind of standardize my code. I'm going to take my same final regression and run that again, but this time on the no out data set. Now that's exactly the same, but let's pretend like we eliminated some people. Normally I would tell you to check additivity. Additivity is going to be important if you have multiple covariates that aren't part of the interaction. But if you have just moderation, we kind of know we have additivity. That's actually an easier way to do it than the code I have here. Right, so if you want to look at the correlations, what we can do is do summary of the output, and then correlation equals true. And so that'll give us the correlation table down here at the very bottom. Now we don't have any outliers, but we're still checking our assumptions here. So I don't know if I want to look at this quite yet, but I can check here just to make sure my coefficients aren't too correlated. And what you'll see is if you ran this on the regular variables and then ran it on the interactive variables, you'll see how this has tampered down the multicollinearity created when there's an interaction added. And so that's one way to do it. I kind of like this way in regular regression because I am not tempted to look at the correlation between X and Y, which is what I want. Plus, it also gives me the correlation with the interaction, so I don't have to manually create that interaction and then toss it into a correlation table. All right. Anyways, but let's check the regular assumptions. Let me clear this stuff out over here. What I want to do is first set up my studentized residuals and my fitted values, so I can use those again here. We're going to create a histogram of the residuals. And they're kind of missing a spot here. They're not the greatest. I mean, it's fairly normal, centered over 0, but we're kind of missing something here. And so this may be because the data is not censored, but is restricted in range because you can't go below 0. And there might be some holes in the data that we're missing because this is a little odd. I can look at my linearity. I mean, it's okay. It's not perfect, but it's pretty close to that line, especially for a small data set. The homogeneity and homoscedasticity. Create myself a plot here. Now I have to remember that the plot is only 1 to 2, so everything's within sort of a normal z-scores range, but there is more, it's more spread out on the right than the left, which is not great. But up and down, it's fairly even spread. And so that may be why we're missing that hole in the histogram, is because there's nobody out here at -2. Further, for homoscedasticity, this is a pretty even spread all the way across. So I would say these are pretty good. Remembering that, it might be a little iffy, but I think a non-parametric analysis would give us the same results here. But we could always try it. A really great function package for that would be rfit package. Now, I'm doing my final model here, which is the same model I've been doing, but now I'm officially looking at it. And what happens is I want to look down here at the main effects. So books is a significant predictor of grades. So for every book we read, we're getting a 4-point increase in grades. And then remember, that's centered. So what that means is that when attendance is average, not when attendance is 0. So that's what I mean about the interpretation gets a little tricky, because normally predictors are when everything else is held constant, aka 0, here's what the influence of books is. But here at average attendance, books is 4 points. So for every one book, we have 4 points on our final grade. For attendance here, when books are average, right? So when they're reading 2 books, which we said was the average, every class we attend is 1 point, and that's significant. And then I can't really interpret the interaction B value. I have to break it up. But the interaction is also significant, which is what we were really interested in. Okay. So if that interaction is significant, we're going to create what we call simple slopes. Simple slopes are, don't think about this as separating into groups. We don't separate this out because we don't want to split variables up. So it's really tempting to think, well, I'll just create thirds or fifths or a median split. Heavens help, don't do that. But what we're doing is we're still using the whole continuum of the variable, but we're going to kind of pretend like people are moved up and down. So we're creating slopes as if we had separate groups, but we're not really separating them. So I'm using the word split here in quotes because we're not splitting, but we're creating different kind of moving the data around to see what would happen if everybody had high scores, or what happens when there are only low scores. So we're just shifting around the regression to look at specific areas of the regression. So traditional is to do this 1 standard deviation below the mean and 1 standard deviation above the mean. I've also seen people do 2 above and 2 below. Kind of depends on the range of your data. This data is not very large in range, so 2 up and down wouldn't make a whole lot of sense. But if you have data that's like really wide, I might suggest 2 in each direction. And this is the part that confuses everyone. So when I want to create my low group, so I'm going to pick 1 variable to split and 1 variable to analyze. And so I'm going to split on books because books are pretty tangible. So people who are only reading a low number of books, people who read an average number of books, and people who are basically reading all the books. So to create my low group, I'm going to take my books. Remember, keep with the Z. I have Z. This isn't really Z, but you get the idea. And we're going to take the low group and move them up to average. Since we've centered our data and 0 is the middle, what we do is we take all of the scores and shift them up, which means that we're interested in what happens when all the other variables are 0. And so what we're doing is creating the low group by moving them up to the middle. So what happens when we pretend they're average? And so we're adding a standard deviation. I know that seems totally backwards to take a group to create a low score by adding a standard deviation, but I wish you could see me gesturing because what you're doing is you're moving people at the bottom to the middle. So you got to bring them up to average. Same thing but reversed with high scores. We want to take the high scores and move them down to the middle. So we're bringing them down to average. The whole thing is shifting where is average or where is 0, which allows us to look at those slopes just for that one split. That it's not a group, that one area of the graph. Okay. So they're called simple slopes. It's very similar to ANOVA simple effects because we're analyzing one variable in the interaction and changing the levels of the other variable. So what I've done is created a low and high regression equation. Okay. It helps if you run the creating those variables first. Okay. And all I've done is taken the original regression equation and changed out low and high. Now, I could show you some analyses that have five-way interactions where you're working on splitting up I don't recommend this really, but where you're working on splitting up the variables. And let's say you have a three-way interaction. What you want to do is split the variable and look for the two-way interactions. If those are there, split another variable and look for those interactions. So you're creating this kind of hierarchy where you break down the variables one at a time. Very similar to ANOVA. If you get a three-way interaction, you split one of those and run the two-way ANOVAs. It's the same idea, but it can get quite complex if, for this one group, these variables are significant, but this other group, they aren't. And so kind of tell you to create yourself a flow chart of like, this group was significant here, and that just helps make it make sense to everyone else. But what I want to do is I'm going to create my summary of the low group, and I'm going to especially look at the variable I did not change. Okay, so what you'll see is the variable I did change doesn't change. That sounds really confusing, but what happens is zbooks here, all we're doing is linearly shifting it around. So its b value should not change. The interaction as well, because it's part of that interaction. So those two variables should not change their significance or their b values, unless something else is weird is going on. And when you get into multi-way interactions, that gets tricky, but the variable that you're changing should not move. So if I look at the summary for the average, it's 4.15 and 0.73. If I look at the summary for high, 4.15 and 7.3. So that should stay consistent. What is changing is the other variable. So I used to tell students to think about, I have one to split and one to flip, and one to analyze. The flip one was the one to split, which one to analyze. And so I'm looking at attendance now. So when books are low, so students are not really reading the books, so they're at on the lower end of the scale. Attendance isn't important. So for when they're not reading the books, going to class is not helping them. Okay. For when books are average, so I'm reading an average number of books, every one class increases my grade 1 point. So I have to have a little bit of those books being read to really get something out of class. Now let's say I'm reading all the books, so when books are high, I'm really getting stuff out of class. So we're creating this fan effect where attendance is now 2 points for every class I go to. So we're going from 0.28, where it's not doing anything for me, so I haven't read the books and class isn't helping, to I've read some of the books and class is helping, but every class is 1 point, and I've read a lot of the books and every class is really helping, it's 2 points. So what you should see in interactive effects is that the slopes are different, and usually it's a fan effect. Sometimes they're positive and negative together, but often they're all positive or all negative. They're just different strengths. So it's very similar to looking at the effect sizes for different effects in ANOVA, where maybe the effects are all in the same direction, so everybody's score is going up, but they have different strengths. So simple slopes is that idea of different slopes for different areas of the regression. Okay. And so often these interactive slopes create some heteroscedasticity. It looks okay here because we've included the interaction in a graph, but when I'll cover latent growth models in my structural equation modeling class, one problem that you might have is that there's this other hidden variable that creates this weird fan in the data, and that is probably due to an interaction that you're just not seeing. So one comment on heteroscedasticity in graphs is that it might be an interaction that you just don't know is there. In our case, we're studying the interaction, so we do hope it's there. But that's how you would analyze monoration graphs by hand. If you only have two variables, quantsci is a really great and simple package. If you have more than that, you like to have a little more control. I have not found a good way to make these graphs. I always still make mine in Excel. So maybe I have some good tips on how to make simple slope plots in R. I am all ears. But that's how to do moderation, complete with data screening by hand in R.